stop scrolling. I have a challenge for you, and I need you to be honest. Before I show you the Hubble images that NASA just released, I want you to go to the comments right now, type your city, and answer this simple question. Do you trust your eyes or do you trust the map? Because what I am about to show you has split the internet in half. One side sees a glowing green ship firing a retro thruster to slow down. The other side sees a trick of the light caused by a simple camera filter. Pause the video and leave your vote. Type Team Ship or Team Dust. Then watch the next 60 seconds and see if you change your mind. Because the difference between an alien probe and a pile of dirt might just be the filter you are looking through. Are you brave enough to see the raw data, or do you prefer the fantasy? Let's find out. We live in an age where the line between scientific discovery and science fiction has become dangerously blurred. Over the last 2 weeks, something remarkable has happened, not just in the sky, but down here on Earth. A narrative has taken hold, fueled by grainy screenshots, processed JPEGs, and the desperate human desire to believe that we are not alone. The subject of this obsession is 3I Atlas, the third interstellar object ever confirmed to pass through our solar system. For the general public, the story is thrilling: a potential craft, a probe, a visitor, performing maneuvers that defy physics. But for the astronomers and data analysts working in the quiet, climate-controlled rooms of observatories around the world, the story is very different. It is not a story of aliens. It is a story of photons, geometry, and the treacherous nature of human perception. To understand what is really happening, we have to slow down. We have to turn off the hype machine and walk into the data itself. Imagine for a moment that you are sitting in front of a monitor at a ground station. The file you are downloading contains the latest observation of 3I Atlas. The internet is already buzzing with rumors that the object has split or ignited or changed course. You open the file, the first thing you see is the raw, unprocessed reality. This is our starting point, the baseline truth. In this first clean image, captured by a standard ground-based telescope, the object sits in the center of the frame like a smudge of chalk on a blackboard. It is a compact, fuzzy dot. This is the nucleus, the heart of the comet, hidden deep inside a cloud of gas and dust called the coma. If you look closely at this raw image stripped of all the filters and digital enhancements, you notice something important: silence. There is no drama here. There is no sharp laser-like jet shooting out to the side. There is no dark cavity suggesting a chunk of the comet is broken off. There is no debris field. In its natural state, 3I Atlas looks incredibly, almost disappointingly normal. It looks stable. It looks like a dust-dominated object behaving exactly as physics dictates it should. This image is the control group. It is the anchor. No matter what wild theories spin up later, and we have to remember that when we look at the object with clear eyes, it appears to be a standard, intact traveler, but a single image is just a snapshot in time. So to really understand 3I Atlas, we need to see how it moves. We switch to the second set of data, the tracking images. These look different, and the background stars, usually sharp points of light, are smeared into long, glowing streaks. This happens because the telescope has stopped tracking the rotation of the Earth and has locked onto the comet itself. 3I Atlas is moving at incredible speeds, falling away from the Sun, and the telescope is panning to keep up. In these tracking shots, we are looking for change. Space is a violent place. If 3I Atlas were a fragile, loosely packed pile of rubble, which many comets are, the stress of its journey should be tearing it apart. We should see the coma warping, or the tail flickering, or pieces drifting behind it like crumbs. But as we flip through images taken on different nights by different observers from different continents, we see something else. Consistency, the coma stays tight, the dust remains aligned. The profile of the object is rock solid. It isn't tumbling wildly or shedding mass and explosive bursts. It is enduring. This consistency is the first real clue. It tells us that whatever 3i Atlas is, it is structurally sound. It is handling the thermal stress of our sun with a resilience that is surprisingly boring and yet scientifically fascinating. Then comes the seduction. And this is where the story usually goes off the rails for the casual observer. We start applying false color. Now, the term false color sounds deceptive, like we are faking data, but in astronomy, it is a tool. Our eyes are terrible at seeing subtle differences in shades of gray. So scientists assign colors to different levels of brightness to make them pop. A faint gray becomes deep blue. A slightly brighter gray becomes neon green. The brightest white becomes angry red. When we apply this map to 3i Atlas, the image transforms. Suddenly, the fuzzy blob looks like a complex swirling storm, and the dust environment appears asymmetric. One side of the coma is glowing hot and bright, while the other fades away. To the untrained eye, this looks like a smoking gun. It looks like an engine exhaust or a directed energy release. The internet sees this and screams propulsion, but the analyst sees something much simpler, geometry. The sun is shining from one direction, the object is moving in another, the dust is flowing in a stream. Of course, it isn't a perfect circle. A comet is not a light bulb. It is a physical object interacting with solar wind. The asymmetry tells us the dust is directional, but it does not tell us why. It is a hint, not a conclusion. This brings us to the villain of our story, or perhaps the misunderstood hero, the Larson-Sekanina filter. If you've seen the viral images showing a sharp needle-like spike pointing directly toward the sun, the famous antitail, you are looking at the work of this algorithm. The Larson-Sekanina filter is a mathematical process designed to erase the smooth, boring glow of the coma so we can see the faint, sharp edges hidden underneath. It is like turning up the sharpen slider on a photo editor until the noise becomes green. When applied to 3i Atlas, the filter produces something shocking. A distinct razor-sharp beam appears to shoot out from the nucleus, pointing towards the sun. It looks impossible. Comets are supposed to have tails that point away from the sun, pushed back by solar wind. A sunward spike looks like a retro rocket, a braking thruster firing to slow the object down. This is the image that launched 1,000 conspiracy theories, but here is the translation for the rest of us. This is a projection effect. It is an illusion of perspective. Imagine you are standing on a highway overpass, watching traffic. If you look down at the cars, you see them spaced out. But if you stand right in the middle of the road, safely, of course, and look toward the horizon, all the cars look stacked on top of each other, forming a solid wall of metal. That is what is happening with the dust of 3i Atlas. This object releases large, heavy grains of dust. Because they are heavy, the solar wind can easily blow them away. So they drift lazily behind the comet, staying perfectly flat in its orbital plane. When Earth moves into a position where we look across that plane edge on, like looking at the side of a dinner plate, all that dust stacks up, and we are looking through millions of miles of dust all at once. To our eyes, and especially to the Larson-Sekanina filter, it looks like a dense, solid beam. The antitail is not a jet. It is a traffic jam of dust seen from a specific angle. The filter makes the geometry impossible to ignore, but it doesn't create new physics. It reveals the structure of the trail, not the presence of a drive. And finally, we arrive at the ultimate judge, the Hubble Space Telescope. Getting time on Hubble is difficult. It is the most precious real estate in astronomy. But for an object like 3i Atlas, the doors are opened. Hubble looks at the universe from above the atmosphere, free from the blur of our air. It offers a view that is crystal clear. If there were a ship, a tiny metal construct, or a swarm of mini-probes buzzing around the nucleus, Hubble would spot the anomaly. We download the Hubble data, and we zoom all the way in, and what do we find? We find the exact same thing we saw from the ground, only sharper. So we see the same orientation, we see the same directional dust flow, and we see the same sunward alignment caused by the orbital plane. Even the mysterious dark lane or depression in the coma, which some theorized was the shadow of a solid hull, resolves into a simple gap in the dust fan. Hubble confirms the ground-based reality. It tells us that the structures we saw in the grainy photos are real, but they are natural. They scale down perfectly. There is no hidden machinery revealed at high resolution. Only more dust, more physics, and more consistency. So where does this leave us? If you look at these images in isolation, it is easy to build a fantasy. You see a streak and think speed. You see a spike and think thruster. You see a color shift and think energy. But science is not about looking at one picture. It is about looking at the movie. It is about the progression. So when you line up the raw data, the tracking frames, the full-scale maps, and the Hubble deep dives, a coherent picture forms. 3i Atlas is a traveler from another star. Yes, it is ancient, yes, but it is not a machine. It is a structured, dust-dominated object that is governed by the same laws of gravity and light that rule our own solar system. It is stable across time, stable across observers, and stable across instruments. This realization might feel like a letdown to some. We want the aliens, we want the third iteration, we want the excitement of a cosmic audit. But there is a different kind of wonder in the truth. Think about what we're actually seeing. And this object formed around a star that might have died billions of years ago. It was ejected into the freezing void, drifting in total darkness for eons, untouched and unseen. It has traveled distances our minds cannot comprehend, only to fall into our little patch of light for a few brief months. And in that time, it has heated up, released its ancient dust, and shown us a structure that is geometrically perfect. The fact that it creates an anti-tail illusion is just a quirk of our relative positions, a cosmic coincidence that we happen to be in the right place to see it edge on. The consistency of the data is the real discovery. It tells us that the physics of the Milky Way are universal. The same forces that shape the comets in our backyard shape this visitor in a nursery far away. We don't need to invent exotic technologies to explain it. The universe is capable of creating breathtaking, confusing, and precise structures all on its own. So the next time you see a viral thumbnail with a neon green comet firing a laser beam, remember the detective work. Remember the raw image, the silent fuzzy dot that started it all. Remember the geometry of the dust plane. And remember that sometimes the most exciting thing an object can do is exactly what physics predicts it will do. 3i Atlas is leaving us now, heading back out into the dark. But it has left us with a lesson. Always check the raw data, always question the filter, and never underestimate the power of a simple pile of dust viewed from the right angle. The investigation is not over. We will keep watching it until it fades from view, and the mystery of the impossible images has been solved. It wasn't aliens, it was perspective. And in a way that is just as beautiful. It's unsettled, it's evolving, and it's definitely not just a rock. Stay curious, stay skeptical, and keep your eyes on the skies. Subscribe for upcoming space updates.